So one of the topics we need to talk about when we're talking about environmental physics is the idea of energy density. We're talking about fuels themselves. Um, they have so many joules per kilogram, and we refer to that as energy density. Now, to give you some idea of some of these numbers, I went ahead and wrote down just some of them. So we're talking about fusionable material. Look how much energy, and this is in megajoules per kilogram. So 1 kilogram of that is going to give me what? 30 million megajoules. So add 6 more zeros behind that, and that's how many joules we have. So fusionable material is huge. Uranium, 90 million megajoules. 42.6 or 46.9 for gasoline. Biofuels, 42.2. Coal, what, 32.5, and wood, 17.0. So you can see when we're looking at energy densities, first thing you got to realize that it's going to be joules. In this case, my scale is megajoules per kilogram. Okay, and we have the problem with a basic energy density chart is that we don't take into account a lot of things. So fusionable materials in uranium seem to have a tremendous amount of energy per kilogram, and they do. The problem with fusion in uranium is that there's a lot of energy that's gone into getting that energy out. Okay? Now, mind you, the trade-off is huge. We get a lot more energy out of it than we do when we put it in, but there's still energy that goes in per kilogram to get fusionable material. To get uranium-235, there's a lot of energy that goes into it. So the idea of energy density has to be tempered with this idea of efficiency. And the Sankey diagrams, I think is how we pronounce them. And how, the process of producing fusion material may only have a 30% efficiency. So only 30% of that energy is actually used, or is actually gained out of the system, I should say. It's all kind of used, but it's only like 30% is actually used, depending. Now, mind you, I'm just talking on my butt about that 30%. But it's important to know that these numbers look awesome, but it takes energy to put them in. Now, the important one I wanted to talk about briefly is biofuels. Now, biofuels is the big up-and-coming thing. We've been talking about biofuels for decades now, and how we need more ethanol, how we need to be converting soybeans and corn into gasoline. The problem with biofuels is efficiency. There's a tremendous amount of energy that goes into producing 1 kilogram of material. So the amount of new energy, if you will, the amount of energy that we get out of it that is new, which is greater than the amount of energy that we put into it, is actually pretty small for biofuels. Now, the next generation of biofuels, when we talk about the super biofuels, in particular the algae-based biofuels, the reason that we're excited about algae-based biofuels is that there's less energy to go in to converting algae into gasoline than that is for corn, for soybeans. I mean, think about corn. You pluck the corn, you husk the corn, you do all this stuff to the corn. You take the corn, you turn it into a mash. You sift the mash through. Then you have to separate the material out of there to the usable portion and the unusable portion. Then you run that usable portion through a series of enzymes and chemicals to get it to gasoline. That's a lot of steps. So with algae, we're hoping, well, first of all, you don't have to strip and mash the thing. Instead, we're hoping these new super biofuels, it goes straight into a chemical process, and those chemical processes are short. So the biofuel will actually be more energy efficient. It may only produce something like 40 megajoules per kilogram, but may only require maybe 10, maybe 5 megajoules per kilogram to produce. So we're gaining a lot of energy out of it. That's why we're excited about it. Now, things that are missing from here obviously are like solar energy, because solar energy is not going to be measured in joules per kilogram, but the amount of energy that we get out of a solar panel, you got to remember that that's not free energy. There's energy that goes into building and installing solar panels. Every ounce of that energy needs to be accounted for to determine whether something is efficient or not. So nuclear power is great, but there's a lot of energy that goes into it. As a matter of fact, the European countries have gone to nuclear because they found sources they have found good sources of uranium, excellent sources of uranium. So there's little energy that goes into producing material for reactors. The United States is not their energy because we don't have great sources of uranium. The uranium that we're pulling is uranium, and it takes a tremendous amount of energy to get low-grade uranium into fissionable material. So the trade-off isn't as great in the United States as it would be in Europe because the amount of energy that goes into producing that kind of that material to get it in there. So that's energy density, and the important thing about energy density is like numbers look good, especially biofuels. Biofuels look really good if you just look at energy density. But the other component that you have to realize is that there's an efficiency. There's an amount of energy that goes into producing 1 kilogram of this material. And that number is equally as important as the amount of energy that you get out of it, sorry. So the amount of energy that you put in is just as important as the amount of energy that you get out of it to determine whether it's a usable source of energy.